Hey physics students, Campbell here. I just wanted to briefly review RC circuits. You're doing this in lab this week, but I thought it was good to actually maybe summarize what's going on. Now, an RC circuit is a circuit that has a resistor and a capacitor in it. And what you should be seeing in lab is that the current is changing over time, right? As we start with initially uncharged capacitor and we build up charge, the current begins to decrease. And then when we discharge the capacitor, again, the current begins to decrease until it becomes zero. And the rate at which this charging and discharging happens actually depends both on the capacitance of the capacitor and the resistance of the resistor in the circuit. So if we start off by first looking at charging a capacitor. So here I have a circuit diagram that shows a battery and a switch. And here's a resistor and a capacitor. Initially, the switch is open and it hasn't been charged yet, so there's no charge on the capacitor, and obviously there's no current flowing through it because I have the switch open. But as soon as we close that switch, what happens is initially at t equals 0, there's 0 voltage across the capacitor. So therefore, all of my voltage, the voltage of the battery that is the voltage that's across that resistor. And the current that initially flows through the circuit is the amount of current that would flow through the circuit as if this capacitor wasn't here. So the current would be the voltage of the battery divided by the resistance of the resistor, because it would be like a simple circuit. The thing is, though, as charge begins to build up on the plates, the current begins to decrease through the circuit. So as time goes by, charge transfers from one plate to the other through that resistor, the switch, and the battery. And as it charges, the current will decrease until the parallel plate capacitor, until our capacitor becomes fully charged. When this happens, the current goes to 0. Now, the equation actually that it talks about this current as a function of time is that initial current, so the voltage of the battery divided by the resistance times E raised to the power of negative the time that we've closed the switch at, divided by the resistance of the resistor and the capacitance of the capacitor. That RC is actually a very important thing, and it's called the time constant. Sometimes it's symbolized as a tau. But that is called the time constant of the circuit. So the resistance and the capacitance will dictate how long that current is flowing, how long the charge is flowing in the circuit. In fact, when the time equals RC, so the value of the resistor times the value of the capacitor, some important things have happened. Charge has increased to 63% of its final value. Current has decreased to 37% of its initial value. So at time RC, there are some definite things going on in my capacitor, no matter what type of capacitor I have. When I get to a time of 10 times the time constant, then current is virtually 0. I mean, it's like 0.000000045 or something like that. So of the initial. So almost 0. Now, a couple things that you need to remember about a capacitor. You need to remember that when we first close the switch and charge a capacitor, the whole circuit behaves as if its capacitor is not there, that it's just a connecting wire. But a long time later, so a long time after that switch is closed, the capacitor then acts like a broken wire, like we've disconnected the circuit completely because no more charge flows. So initially in the charging process, it's like it's not even there. Electrons are flying. But as it charges, those electrons are feeling more force of repulsion, so that current slows down. And then after a long time, it's as if I just unhook the whole circuit because there's no more current flowing. It can't. The capacitor's full. Now, what about discharging? When I discharge, say I remove the battery from the circuit and I make a closed loop that connects my resistor and capacitor, well, now current's going to actually flow the opposite direction. In fact, we call that like a negative current, because maybe if it was going this way when I charged it, it's now discharging, so going the opposite direction. Now, initially, the current is the maximum, what it was when I first flipped that switch to charge it in the first place, but it eventually decreases to 0 as I run out of charge on my plates. Now, that time constant, RC, plays an important role in discharging as well. When I'm discharging, and notice here's a graph of current versus time, notice it's negative because it's flowing the other way. Not that it's a negative current, it's just flowing in the opposite direction as it did when we charged it. But notice here, when I get to RC, I'm at 37% of that initial current. Same thing with charge. When I get to the time of RC, so the resistor times the capacitor value, I am at 37% of my initial charge. So that time constant actually tells us about when I'm going to have a certain amount of current or a certain amount of charge on my capacitor, whether I'm charging or discharging. So that time constant, RC, can help us when we're designing a circuit if we want to have the current last for longer, or if we want it to go quickly. Then we can use our time constant, the resistance times the capacitor. We can use the ideal setting that we want to determine what type of capacitor and what value of resistor we should put in our circuit. Well, hopefully that helps clear up some of the stuff we're going to do in lab this week. I'll see you in class.